Hello, good morning. Discuss about the electric field, and it is the second class of physics 2. What is electric field? So today we'll discuss what is electric field, and it is denoted by capital E, and in vector form this will be this. That means what is electric field and determining how to determine the electric field. Okay, so we'll discuss two experiments and some real life examples of electric field. So first of all, what about the concept, basic concept of electric field? First of all, the concept of the electric field. The field model explains how the force due to charges is transmitted through empty space from one charge to another. This is actually real life example. And this figure shows pen, a shallow pan of oil with grass seeds floating on it. And when positive and negative air touches oil, a pattern emerges. That means this is a pattern and some force line of force producing. And due to this line of force, an electric field produced. Some kind of electric influence, from the charges fills the space around the space. Then the concept of the electric field. In the force model of the electric field, the positive charge A, this is the positive charge, A exerts an attractive force on charge B. So this F vector, that means force A on B, in graphically we can denote A exerts an attractive force on charge B. In the force model, A exerts a force directly on B. So the concept of the electric field in the field model, it is the alteration of space around the charge A, that is the agent that exerts a force on charge B. Okay, this is the A charge and this is the B charge. The alteration of space, what is we call a field. Okay, the alteration of space, it is called also a field. The charge makes an alteration everywhere in a space. So actually we are discussing the field model. In the field model, alters the space around it. The wavy lines are poetic license. We will soon learn a better representation that. So the concept of the electric field, there are three types of field. In the space around a charge is altered to create an electric field, and the alteration of space around a mass is called the gravitational field, and the alteration of space around a magnet is which is called magnetic field. So we have to remember these three types of field. One is electric field, second one is gravitational field, and third one is magnetic field. So due to this, we have discussed in our first lecture of this physics 2, we have discussed about the two field. One is gravitational field and another is vector electric field. So we are reviewing some concepts of this. So in our previous lecture, we discussed about Coulomb's law, and so the Coulomb's law versus Newton's law of gravity. This is the actually mathematical representation of Coulomb's law from Q1 charge and Q2 charge. If their distance is r, then we get the force between these two charges like this. And the gravitational field, if the mass of Q1 is m1 and the mass of Q2 is m2, then capital G is the universal constant of gravitation. So we get, this is the gravitational force. So there are two, in these two force, there are many difference. First of all, attractive or repulsive. So Coulomb's law will be attractive for the opposite charge and repulsive for the equal charge or like charge. And we have to remember that the gravitational force always attractive. And 1 by r square, 1 by r square, same distance is square, inversely proportional to the square. And remember that we have calculated in our previous lecture, Coulomb's law of force. Force will be very strong and very weak force. Gravitational force is very weak because E square divided by 4 pi epsilon is this is more and more greater than minus gm square. So only relevant relatively local scales and important on every large scale planets and the whole universe. And the whole universe, there are many planets, um, substance. Okay, so this gravitational force acts on that, and only relevant relatively local scales. Okay, so this is actually Coulomb's law versus Newton's law of gravitation. So the electric field actually we are discussing what will be the electric field. Physicists did not like the concept of action at a distance. That is, a force that was caused by an object a long distance away. They preferred to think of an object producing a field and other objects interacting with that field. So this is the positive and this is the negative. That's rather than they like to think like this. Actually, it is very simple to see, but the physicist thinks like that. So the electric field E is defined as the force acting on a test particle divided by the charge of that test particle. That means electric field is the force per unit charge. Force per unit charge. So force per unit charge is called the electric field. So if this is the Q and this is the Q naught, and their distance is R, so the electric field from Q to Q naught is given by capital E, and the acting force is capital F. So this electric field E is denoted by F by Q naught. From the Coulomb's law of charges, we can convert this F into, by using Coulomb's law, we get capital E equals to 1 by 4 pi epsilon naught Q divided by R square, R, and this is the vector form. Okay. So the electric field of a single charge like this, this distance is R, and electric field from positive charge to Q naught. So this is the repulsive force. So electric field from isolated charge and electric field from test particles. Okay. So this is the actually the real life example of electric field, which is defined everywhere, even if there is no test charge is there. So charge particle in electric field, using the field to determine the force F equals to QE. Okay, from our previous, from the definition of electric field, we get capital E equals to F by Q. Then, so this is the line of force from positive charge, and this is the negative charge. So F equals to QE, and this force acting for this Q, and this F equals to QE is acting for the negative charge. So from this point of view, what is the actually electric field? So we can define the electric field like this. The electric field is a region of a space around a charge or a system of charges within which other charged particles experience electrostatic force. So theoretically, electric field extends up to infinity, but practically it is limited to a certain distance. The electric field strength or electric field intensity or electric field. The electric field strength, strength at a point in an electric field is the electrostatic force per unit positive charge acting on a vanishingly small positive charge placed at the time. Suppose at the point. Suppose Q plus Q is the point charge, another point charge plus Q naught. So their repulsive force will be capital F. Similarly, for the negative charge Q and the positive charge Q naught, this is also attractive force capital F. So Q is the source charge and Q naught is the test charge. That means we are testing this Q naught whether it is repulsive or attractive. And we are evaluating the electric field. So capital F is the force and E is the field. So capital will be limit del Q tends to 0. If del Q tends to 0, then F by del Q, we get this ratio. Okay, this ratio will be the electric field because this ratio denotes the per unit charge, force per unit charge, and del Q is very small. So after omitting limit, we can write E equals to F divided by Q naught. That means test charge. Q naught is the test charge. So force per unit test charge is called electric field, or capital E equals to, we can denote this capital F by using Coulomb's law from our previous lecture, 1 by 4 pi epsilon naught Q by R square, and this is the vector form. Okay, so the test charge is considered to be vanishingly small, very small, tends to 0, because its presence should not after the configuration of the charges, and thus the electric field which is intended to be measured. So this is the actually mathematically we can denote the electric field. Since Q naught is taken positive, the direction of the electric field is along the direction of the electrostatic force. So the force will be electric field force and direction of force will be same. The electrostatic force on a negatively charged particle will be opposite to the direction of the electric field. So you have to remember that if there are negatively charged, if we place the test charge as a negatively one, then that will be the opposite, the opposite direction. Electric field direction will be opposite to that of force. So the electric field is a vector quantity whose magnitudes and direction are uniquely determined at every point in the field. So the SI unit of electric field is Newton per Coulomb. You have to remember it, Newton per Coulomb. So the electric field due to a point charge, force exerted on the test charge Q naught by Q. So capital F equals to 1 by 4 pi epsilon naught Q naught divided by R square, and this is the vector form. So this is the three-dimensional X, Y, Z. Then if we can, this is the origin. So this is the origin. If we this is the point P X Y Z. So if we place a point charge or a test charge plus Q naught, and the distance between the Q charge, another charge will be plus Q. This is the source charge. So their distance between will be R. Then we get capital F equals to, that means acting force between these two. By Coulomb's law, we can write F equals to 1 by 4 pi epsilon naught Q naught divided by R cube. And this is the vector form. Okay. So electric field strength, from our previous slide, we get the definition of electric field equals to force per unit test charge. Okay, force per unit test charge. That means F by Q naught in this case. So electric field around this length R, around this distance between R will be what? 1 by 4 pi epsilon Q by R cube. Just putting the value of F here. Okay, putting this value of Coulomb's law. By Coulomb's law, we get this force, and putting this F, we get this formula of electric field. So this electric field can be written as 1 by 4 pi epsilon naught Q by R square, and without vector form. But there is a mistake for you. This will be only Q by R square. So the electric field due to a point charge has a spherically symmetry. If Q greater than 0, that means if charge is positive, then the field is radially outward. Field will be outward. Field will be outward. This is the outward. And if Q less than 0, then the field is radially inward. We have to remember these two conditions. If charge is positive, then it will be outward, and if the charge is negative, then we get this one. So in the vector form, the electric field can be shown by this way. If R equals to x square plus y square plus z square square root over, if R equals to square root over x square plus y square plus z square, from this X distance will be x square, y distance will be y square, and z distance will be z square. So r square equals to x square plus y square plus z square. So in this case, we can write r equals to this one, and this is the vector form will be xi, yj plus zk, three-dimensional vector. So by superpositional principle, the electrostatic force experienced by a charge due to other charge is the vector sum of the electrostatic force due to these other charges as they are existing individually. So capital F equals to F force along 1 to 2, charge 1 to 2, and F13 will be charge force from charge 1 to 3. Okay, from this figure we can write this sum of all forces. So we can explain the electric field in this way. So in this point of view, actually what is electric field? An electric field is an individual force field that affects the electric charges. The field is defined on based on how it affects a positive test charge. That means Q naught. All charged objects are assumed to have an electric field associated with them. So the electric field mapping, this is the positive charge and this is the outward. Okay, force will be outward. And this is the negative charge, force will be inward. So this is the graphical depiction. So electric field around a positively charged will be like this from A to B. Okay, this is the positive charge and this is the P is the test charge. Then electric field will be like this. An electric field around charged pair. Suppose negative and this is the first charge is negative and second charge is positive, and the force will be outward from positive charge and inward in negative charge. Okay, but here positive the electric fields will be like this. This is the positive charge and this is also here attraction will be repulsive at repulsive force. This is why electric field will be electric line will be like this, force line. This is the electric field line. Due to this electric force line, electric field produced. Now electric field of a set of parallel plates. Suppose this is the positive one and this is the negative one. So their distance will be small d, and a polar form will be created. So electric field mapping rules: E field lines must never touch or cross themselves or other field lines. Electric field lines run out of a positive charge and into a negative charge. That means outward from positive charge and inward in negative charge. The electric field lines must intersect charged object at a right angle. Okay, this is the important properties of electric field lines. The number and density of lines indicates the field strength or intensity. So we are measuring, actually we are discussing about the electric field, and this electric field will depends on number and density of lines indicated field strength. So the electric field intensity will be capital E equals to capital F force per unit charge. So Q represents charge or test charge. Remember it. Units of electric field intensity are the newtons per coulomb. So an electric field equation for point charge will be like this by using Coulomb's law. So electric potential energy. Electric potential energy is the energy stored within an electric field. The work done in moving a charge within an electric field is equal to the potential energy stored. So potential energy can be measured with the help of electric field. The kinetic energy gained by a charged particle within an electric field is equal to the potential energy lost. That means potential energy lost equals to kinetic energy gain. So what are the units of electric potential energy? EPE, electric potential energy. And we have discussing about this line of forces of electric field from A to B. So work done, work energy theorem, by work energy theorem, we can, this is the electric potential energy and electric kinetic energy will be same. So electric potential is the ratio of the work done on a charged particle within an electric field divided by the particle charge. Units are joule per coulomb. Same. The other term used for electric potential are electric potential difference or voltage. So electric potential will be what? V equals to W by Q. That means work done in per unit charge. Units of electrical potentials are joule per coulomb or volt. Same. Okay. So electric fields within a charged objects like this. This is the positive charge and this is the electric field and this is also electric field and this is the capital R because whole distance and this is the small r just taking the radius. In this part electric field equal to 0. Okay. For the other one volt will be like this. This is the electric potential. Now potential inside a conductor like this. So charged conducting sphere, this is the charge conducting sphere and potential will be V equals to Q divided by 4 pi epsilon naught R. So electric field of a set of parallel plates like this. Similarly, the capacitor we'll discuss it about in our next lecture. Now, how to determine the electric field, determination of electric field. Determination of electric field. So, field due to a long straight uniform charged wire. First condition, field, electric field due to long straight uniform charged uniform charged wire. That means we are trying to find out the electric charge, electric field of a charged wire. Suppose we have a very big length. This is a very big length wire, which is infinitely, and this is any point P in which we are finding the electric field, value of electric field. This is the P point, and this is the where we are discussing about. This is the where we are discussing about, and this is minus infinity to up to plus infinity. So suppose if we take small length dx, and distance of this length will be r. So due to this charge, there are some charges on dx, suppose dq charges. So their electric field will be dE. Okay, and this dE will be effect on. There are two components of this. This is the vector quantity. So there will be one acting on this and another one acting on this. So along the base, this will be dE cos theta. Okay, and along this dE sin theta. So this dE sin theta and this dE sin theta will be balanced. So only the acting components of this electric field will be dE sin theta. Okay, suppose and the electric field at P is due to charge, electric field due to charge will be dq, and this, suppose this dq is the charge. This dq charge, and this is the origin from here, and suppose this whole length will be x. This whole length will be x. So the total charge can be taken as lambda dx. Suppose the whole where charge, total charge will be q. So by the equation we can write dE equals to the acting electric field will be amount of charge dq, suppose dq divided by 4 pi epsilon naught r vector divided by r cube. Okay, or we can write dE equals to lambda dx divided by 4 pi epsilon naught r vector divided by r cube. This is the equation number 1. Again, this is the acting d cos theta along the base. Suppose this is the angle theta. So that the component of dE due to the charge dq. Here the charge how many? dq. So total charge will be again dE cos theta acting electric field due to at point P due to this charge will be what? Equals to lambda 4 pi epsilon naught dx divided by r square cos theta. Okay, just putting this one here by equation this equals to, suppose this OP, here OP equals to A and R is the actually distance from this dx to point P. So this dx equals to, we can write cos theta. So this cos theta below can be written as like this: cos theta equals to lambda divided by 4 pi epsilon naught dx by r square. But this cos theta equals to base divided by hypotenuse. So base equals to what? A, hypotenuse equals to r. Okay, so since cos theta equals to what? From this figure, base by hypotenuse, A divided by r. Okay, so from this we can write lambda A 4 pi epsilon naught dx divided by r cube. And this is dE cos theta. This is equation number 2. So now, therefore, the electric field P at point P, the electric field at point P, we can find out from the equation 1. From the equation 1, total electric field will be EP equals to minus infinity to plus infinity, because the length of wire will be minus infinity to plus infinity, and lambda A divided by 4 pi epsilon naught, and this R equals to what will be, from here, from the figure we can write R equals to R square equals to x square plus a square. Okay, from this figure we can write R cube, R equals to this. So R equals to what will be, from this figure, R equals to root over x square. So R equals to, putting this value, we can write a square plus x square 3/2. Now from this, if we put R equals to x equals to a tan theta, x equals to a tan theta, and the limit value will be minus pi by 4 to minus pi by 4 to plus pi by 4, then lambda a 4 pi epsilon naught a square plus x square. Just putting here x equals to a tan theta. So dx equals to what will be, a sec square theta d theta, and limit will be changed, x, another will be theta. If x equals to infinity, then tan theta will be what, also pi by 2, 90 degree. So this will be pi by 2. And if x equals to minus infinity, then minus pi by 2. Okay, this is why a square plus x square will be what, a square common. If we take a square common, a square whole to the power 3/2 means what, a cube. So 1 plus tan square, 1 plus tan square theta means what, sec square theta. So square cube, so sec cube theta. And dx equals to what, a sec square theta. So d theta. So from here we can write, actually sec square theta will be cancelled, a will be cancelled. So from here we can write, after putting the values, we get a square cancelled. So we get lambda divided by 4 pi epsilon naught a. This is the actually required electric field of air due to a long straight line, straight uniform charged air. So this is very easy calculation for us. If we try to understand, of course we can, but you have to practice for that. You have to practice for that. So from here we get a square will be cancelled, sec square theta cancelled. So 1 by cos theta. 1 by cos theta means only cos theta. 1 by sec theta means what, cos theta. So integration of cos theta, what? Integration of cos theta will be sin theta. And limit will be what? Minus pi by 2 to plus pi by 2. Okay. So minus pi by 2 plus pi by 2. So this equals to, we can write sine pi by 2 means what? Sine 90 degree, 1, and minus sine 90 degree. So this will be only 2. Okay. So 2 will be cancelled. We get lambda divided by twice pi epsilon, twice pi epsilon naught A. So from this integration, we get 1 plus 1. That means 2. So we get actually the required electric field due to a long straight uniformly charged wire. So from this equation, it is evident that in the case of a long straight wire, the electric field is inversely proportional to the first power of the distance from the wire and is not inversely proportional to the square of the distance as in the case of point charge. So for the point charge, actually we get this one, this equation, the electric field at the point P equals to lambda divided by twice pi epsilon naught A. So actually in per unit length, the number of charge will be lambda. In per unit length, the number of charge is lambda. So in the per unit length, the we get the charge is what? Lambda per unit charge. So in dq, the number of charge will be lambda into dx. Okay. By unitary method, we can write also in per unit charge the amount of per unit length. So in per unit length, the number of charge will be lambda per unit length. Remember it, lambda is the per unit length charge in per unit length. Now another one, a field at a point on the axis of charged circular turn of wire. This is now for the circular determination of electric field for circular arc, circular turn of wire. Let us consider the circular turn of wire of radius A. Suppose if we want to draw this circular one like this. Suppose this is the circular turn and this will be radius. And the radius, this is the actually axis. Suppose we are evaluating the electric field at point P. This is the P point and this is the origin. Suppose this is the a particular area we are counting, and this is also radius A. Suppose this angle will be pi. Okay, this is the x and this is the y-axis and this is the z-axis. So in three-dimensional space we are counting, and this angle will be theta, and this distance from the a part of circular wire we are counting this area, cross-sectional area, and distance will be r, and distance from the origin will be b. So the electric field due to this part at point P will be dE cos theta along dE cos theta. And this will be dE due to charge, a small charge dq. Suppose this is the ds area, and you must know this is the circular. So this dE has two components. This vector has two components. One is along the base and another one is along the perpendicular. So dE sin theta and dE sin theta will be balanced each other. This is why the only acting electric field will be dE cos theta. You must know this is the twice pi a. This whole length will be twice pi a. So in the whole twice pi a, there will be charge amount what? Q. So in per unit length, Q by twice pi a. And in ds length, how many charge will be? So the total charge we can calculate. Total charge Q equals to what will be? Q divided by twice pi a into ds. In this length, in the ds length, the total charge will be this. So total electric field what will be? Total electric field and total electric field, acting electric field d cos theta. So total will be the integration of dE cos theta. Okay. Now by the equation we have discussed in our previous slide, dE formula what will be? 1 by 4 pi epsilon naught, and charge will be Q divided by twice pi a ds. This is the amount of charge for this ds, and distance will be from P will be inversely proportional 1 by r square. But here remember that here cos theta equals to what? Cos theta equals to base by hypotenuse. Actually base is B and hypotenuse is R. So base divided by hypotenuse cos theta. And R equals to what will be? R equals to A square plus B square from the figure. A square plus B square. So from here we can write using this relation. If we take the integration, we can write integration dE equals to what will be? Integration 1 by 4 pi epsilon naught Q ds divided by twice pi a. 1 by r square means 1 by r square means what will be? One by r square means this will be from equation this one, equation 1. Cos theta equals to. So this equals to 1 by r square means what? 1 by r means what? Root over a square plus b square. 1 by root over a square plus b square. And cos theta equals to what? B divided by root over s square plus b square. Actually, this comes from equation number 1. So this equals to, we can write 1 by so this can be written as 1 by 4 pi epsilon naught q divided by twice pi a and b divided by s square plus b square. This is the base. Half plus 1 equals to 3 by 2. Integration of ds. But remember it, total distance of this circular pair will be twice pi a. That means circumference. Okay. Total length will be what? Twice pi a. So this can be written as q b divided by 4 pi epsilon naught twice pi a s square plus b square divided by 3 by 2 multiply twice by a. Twice by a will be cancelled. So we can write 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught qb divided by s square plus b square 3 by 2. So this is actually total electric field we are calculating. Total electric field at point P. Okay, acting electric field due to small charge. EP equals to 1 by 4 pi epsilon naught QB divided by S square plus B square. But there is a condition for us. There is a condition depending on the distance. Distance will be if B is more and more greater than A, if B from here, this is equation number 2, if B is more and more greater than, that means distance from the origin A. If B is more and more greater than A, that means if B is more and more greater than A, then we can write the equation like this. Then from 1, then from 2, we can write EP equals to what will be 1 by 4 pi epsilon naught Q divided by Q divided by this QB divided by, then if B is more and more greater than A, then neglecting A, we can write B square 3 by 2. Okay, that means B cube. So B and B cancelled, so we get 1 by 4 pi epsilon naught Q divided by B square. And it is actually similar to the electric field produced by a point charge. Thus, the greater the distance from the charged ring, the more nearly does the field produced by the ring approach that produced by a point charge. That means if we neglect this B, so, this A, okay, because B is more and more greater than, this is why we get the electric field for the circular turn of the earth. So this is actually our required result. Now another important one, the interaction of electric line of forces. An electric line of force is an imaginary straight or curved path along which a unit positive charge is supposed to move when free to do so in the electric field. That means if you place a unit charge on an electric field, and it will feel a force due to some line of forces. So for which it will feel a force. Those are called electric line of forces. Actually, electric line of force will be, suppose this is the electric field, and the electric line of force will be like this. Okay, and we have studied the properties of electric line of forces in our previous slide. Electric line of force do not physically exist, but they represent real situation. We have to remember this. So electric line of force due to a point charge will be like this. If point charge is positive, then line of force will be outwards, and if the charge is negative, then the line of force will be inwards. We have to remember this. Okay, representation of electric field in terms of vector field. The size of the arrow represents the strength of the electric field. You have to remember this. Representation of electric field in terms of field lines, and this will be field vectors. An easy way to drawing, you can represent it. The electric line of force due to a pair of equal and unlike charges, dipole. This is called dipole. What is the dipole? Equal and unlike charges. Suppose plus q and another is minus q. They are equal but opposite charges. Okay, equal and unlike charges or opposite charges, then positive and negative. So the line of force will act like this. That means electric lines of force contract lengthwise to represent attraction between two unlike charges. Electric line of force due to a field of equal and like charges like this. So electric lines of force exert lateral and represent the repulsive between two like charges. So electric line of forces due to a uniform field. So we can discuss this in a broader way, the properties of electric line of forces, which is very important for you. The electric line of forces, are imaginary lines. First properties is, this is imaginary line. A unit positive charge placed in the electric field tends to follow a path along the field line if it is free to do so. The electric lines of force emerge from a positive charge and terminate on a negative charge. Remember it. We have shown in figure. The tangent to an electric field line at any point gives the direction of the electric field at that point. Now the last property is, two electric lines of forces can never cross each other. That means cannot intersect each other. If they do, then at the end of intersection, there will be two tangents. That means there will be two direction of electric field. This is why it means that there are two values of the electric field at that point, which is not possible. This is why the electric line of forces can never be intersect each other. Further, electric field being a vector quantity, there can be only one resultant field at the given point, represented by one tangent at the given point for the given line of forces. So we have to remember these 5 properties of electric line of forces. So the electric line of forces, are closer, that means crowded, where the electric field is stronger and the line is spread out where the line of electric field is weaker. That means like this. Because capital Q is the uh, uh, bigger than small q. This is why there are crowded lines and weaker, and it is stronger and it is weaker because the amount of charge is uh, less than this. So electric line of force are perpendicular to the surface of positively or negatively charged body. We have to remember this. This line of forces outwards because of positive charge, and it will be perpendicular to the surface of this charge. Similarly for the negative charge also. Now, this is the positive charge. So immersed the line of forces, and this is also immersed line of forces perpendicularly from the surface of the charge. Electric line of forces contract lengthwise to represent attraction between two unlike charges. Similarly, electric lines of forces exert lateral sideways pressure to represent repulsion between two like charges. You must know like charges repulse each other. This is why it will happen in the same case of electric line of forces. So the number of lines per unit cross-sectional area perpendicular to the field lines, that is density of the line of forces, is directly proportional to the magnitudes of the intensity of electric field on that region. That means number of line in cross-sectional area per unit cross-sectional area is proportional to the electric field. So electric lines of forces do not pass through a conductor. You have to remember that. Suppose solid or hollow conductor this, and we have to remember that the line of forces do not pass through a conductor. Hence, the interior of the conductor is free from the influence of the electric field. So electricity cannot pass through it. This is why this is a conductor, a hollow conductor. This is why. So electrostatic shielding. This is called electrostatic shielding, and this is positive and this is negative. So electric lines of force can pass through an insulator. You have to remember that electron line of forces can pass through an insulator, but it cannot pass through on a conductor. So the electric what is electric dipole? It is very important for you. In the due to electric charge and a dipole form. So the electric dipole is a pair of equal and opposite charges separated by a very small distance. There is a condition, and this will be equal charge and opposite, but the distance will be what? Very small. The electric field produced by a dipole is known as dipole field. Okay. The electric dipole moment is a vector quantity which is used to measure the strength of an electric dipole. Suppose electric dipole moment P equals to Q multiply twice I. Okay. Here's the I vector. The magnitudes of electric dipole moment is the product of magnitudes of either charges and the distance between the two charges. So quantity of charge, distance between these two charges. The direction is from negative to positive charge. We have to remember that the direction will be positive to negative. Suppose this is the positive and this is negative, and their distance will be twice I. So the SI unit of P is Coulomb meter, because this is the moment, electric dipole moment. So the SI unit will be Coulomb meter. Note, an ideal dipole is the dipole in which the charge becomes larger and the separation becomes smaller and smaller. So an ideal dipole will be created when the charge become larger and larger and their distance will become smaller and smaller. So you have to remember this one. Now, electric field intensity due to an electric dipole. So we have measured actually electric field for a different where length and circular. So at a point on the axial line, resultant electric field intensity at the point P will be equals to EA, electric field at A, and plus electric field at B. So the sum will be give the electric field at point P. Actually, it is a vector representation. So the vectors electric field at A and electric field at B are collinear and opposite. Collinear means it exists in one line. Okay, and this will be opposite because plus and minus opposite. So this EP equals to can be written as, if we change the direction, then it will be EB minus EA, because B is the positive charge. Okay, so it will be bigger. So by using Coulomb's law, we can write electric field at point A will be x plus 1 whole square. Okay. Similarly, electric field at B will be what? X minus 1, because at point A plus 1 and at point B minus 1, because emerged the electric field, the direction will be coming from point B. So the electric field at point P will be this minus this. So electric field point P will be this. So this is the actually calculation at point P by using electric dipole. So electric field at point P will be 1 by 4 pi epsilon naught twice Px x square minus 1 square. So if I is more and more less than x, so then we can omit I. So we get x divided by x. So EP electric field at point P can be evaluated as approximately like this. So xx will be cancelled. So hence the direction of electric field intensity at a point on the axial line due to a dipole is always along the direction of the dipole. Now at the point of the equilateral triangle, the point of equilateral triangle, we can find out the electric intensity. Suppose this is the equilateral triangle A, B, C, A, B, A, B, and Q is the equilateral triangle. So who is the midpoint? So is the median. So at the point Q, the electric intensity at the point Q will be EQ equals to what will be EQ according to the vector electric field at point A plus electric field at point B. Okay, the vectors A and B are acting at an angle twice theta. This is theta and this is theta. The sum of these two will be twice theta. So using the Coulomb's law, we get right this. Similar way, the vectors A sin theta and EB sin theta are opposite to each other and hence cancel out. Okay, this will be cancel out. Only cos theta by along the base will be exist. Okay, along sin theta and along the perpendicular, the electric field will be removed. The vectors EA cos theta and EB cos theta are acting along the same direction. This is why the electric field at point Q can be denoted by EA cos theta plus EA EB cos theta. Similarly, we can denote this cos theta equals to what will be base by hypotenuse. Okay, we get this one. After a simplification, we get this one. This is very important for you. At a point on the equilateral triangle, equilateral line, the resultant electric field, equatorial line. So the electric field at point Q, we get this one. If I is more and more less than y, then we can approximately the electric field EQ equals to this one. So the direction of electric field intensity at a point on the equatorial line due to a dipole is parallel and opposite to the direction of the dipole moment. So if the observation point is far away and when the dipole is very short, then the electric field intensity at the point on the axial line is double the electric field intensity at point of the equilateral line. So if I is more and more less than x and I is more and more less than y, then we can write electric field at point P is the twice the electric field at point Q. So now torque on a electric dipole in a uniform electric field. What will be the torque? The force of magnitudes will be what? Equals to F by Q. This is why force will be F equals to QE, but the charge will be P. This is why P acts opposite each other and hence net force acting on the dipole due to external uniform electric field is zero. So there is no translation motion of the dipole. However, the force are along different lines of the action and constitute a couple. Hence, the dipole will rotate and experience torque. Torque equals to what will be electric force multiply distance. So electric force will be QE and distance will be twice I sin theta. Okay, this is plus Q and this is minus Q. Their distance will be twice I and angle will be theta. So P and QE will be the electric field and emitting the direction will be opposite of negative charge. Okay, this will be the direction of force and force will be what? QE, because electric field equals to F by Q. This is why electric force will be QE and distance will be what? Distance will be twice I sin theta. And now torque equals to the vector form. This is the vector representation. P vector cross E vector. This means cross product. So the direction of torque is perpendicular and into the plane containing P and E. So P equals to moment force along the different lines of action and constitute a couple. Okay, then a torque form. So SI unit of torque is Newton meter. In case of if theta equals to 0 degree, then torque will be 0. Sin 90 degree, sin 0 equals to 0. But if theta equals to 90 degree, that means they are perpendicular to each other, then torque will be highest PE. Highest torque will be PE. So we have to remember that if theta equals to 0 degree, then torque will be minimum and 0 and maximum torque will be at 90 degree. Theta equals to 90 degree. That means if we replace the charge at 90 degree angle, then we get maximum. So if theta equals to 180 degree, then torque equals to also what? 0. You have to remember it. Now, work done on electric dipole in uniform electric field. When an electric dipole is placed on a uniform electric field, it experiences a torque and tends to align in such a way to attain stable equilibrium. That means work done equals to T d theta. T means what? Torque. Okay, torque equals to what was? PE sin theta. Now total work done, what will be? Integration from theta 1 to theta 2. Okay, from theta 1 to theta 2, due to this rotation, the work done will be P sin theta d theta. So W equals to, you can write P and sin theta after putting the upper limit and lower limit, equals cos theta 1 sin integration cos, this is why cos theta 1 minus sin theta. So if the potential in energy is at arbitrarily taken 0 when the dipole is at 90 degree. You must know if 90 degree dipole at 90 degree, we have to take the potential energy as 0. So the potential energy in rotating the dipole and indicating it at an angle theta will be what? U equals to minus P sin theta. P cos theta. Okay, because cos 90 degree equals to 0. So note that the energy can be taken 0 arbitrarily at any position of the dipole. If cos theta equals to 0 degree, then U equals to P. That means a stable equilibrium. If theta equals to 90 degree, U equals to 0. And if theta equals to 180 degree, then U equals to highest. That means unstable equilibrium. You have to remember that U equals to P, then we get unstable equilibrium. So now this is the end of our lecture today. Actually, we have discussed the electric field and electric line of forces, and we compare the electric field and gravitational field. Then we have determined the electric field for a circular, for a long wire, and number two, the determination of electric field for circular turn of wire. Suppose we can discuss some real life examples. Finding the electric field of a proton. Okay, suppose the proton of a charge q equals to the equal charge of electron. At the distance of electron, the magnitudes of the field is, suppose k equals to is the constant Coulomb and meter square per Coulomb square, and E is the 1.60 into the minus 19 Coulomb, and R equals to this distance 5.3 10 to the minus 11 meter. Then we get the electric field like this. Find the electric field of a proton. Because the proton is positive and the electric field is directly away from the proton, and E equals to 5.1 10 to the power 11 Newton per Coulomb outward from the proton, because this is the positive charge. SS, this is a large field, but from the table you can write this one. Electric field of a point charge. An electric field diagram for a positive point charge is constructed by drawing electric field vector at a number of points around the positive charge. All the vectors point straight away from the positive charge, straight away. Okay, straight away. So for the proton, we get the electric field line like this. Okay. And for the negative one, we can find the electric field diagram for a negative charge is drawn with a vector point toward the negative charge. This is the toward, and for the proton away from the positive charge. This would be the direction of the positive force on a positive probe charge. So which of the two sets of electric field vectors is possible? Can you say? Only A possible, only B possible, both A and B are possible, neither A and B possible. Which of the two sets of electric field vectors is possible? So think actually both A and B are possible. Another one, at which of the electric field is stronger? Can you say? Point A, point B, not enough information to tell. Think actually point A. This is the positive charge, and you must know the stronger field will be this, because this is the test charge and this is the source charge. Now rank in order from largest to smallest the magnitudes of the electric field at the black dot. What will be? Can you say? This is the q charge and this is the twice q and this is the twice q, distance r, and it will be the rank, the magnitudes of the electric field at the block dot. Can you say? Actually 3, that means twice q, and 1, then 1, and then for 2, then 2. So you have to think about this. Now all charges shown have equal magnitudes. For case 1 through 4 is the electric field at the dot to the right r, to the left or 0. Can you say? 1 positive negative dot, and 2 negative positive dot, dot positive positive. Which one actually? All charges shown have equivalent magnitudes. Have equal magnitudes. 1 through 4 shown is the electric field at the dot to the right r, to the left or 0. Actually B will be the result. Now all charges shown have equal magnitudes. Rank in order from largest to smallest. The magnitudes of the electric field at the black dot. Electric field will be black dot. So the result will be 1, then 3, then 2. Which is the electric field at the dot? Which is the electric field at the dot? So actually B. You have to remember this. Think about this quiz. I hope you can find out the result. A small bed sitting at the origin has charges of plus 10 Newton Coulomb and Coulomb. At the point 3 centimeter and 4 centimeter, what is the magnitude and direction of the electric field due to this bed? So this will be the finding the electric field near a dipole. In next class, we will discuss about the Gauss law. So thanks to everybody.